the different types of materials processing is smelting, mainly for metals, is smelting, arc melting, sintering, and chemical methods. And I'm not going to go over all of these, but for metals, you need to uh, first understand whether the metals are ferrous or non-ferrous. If it is ferrous, then it can be either steels or cast irons, right? So again, to determine that, you need to understand the phase diagram. And if the carbon content is smaller than 1.4 weight percent of carbon, which is somewhere here, this is all steels, and rest is, if it is above 3.3 to 4.5, this is all cast iron. Okay, so 6.7% is cementite. This is a compound, right? Compounds are represented as lines in your phase diagram. And this is liquid, and here are three phases. That is gamma, that is austenite, alpha, that is BCC, and then you have, so alpha is ferrite. There should be one more, right? Delta, where is it? Oh, here it is, delta. So if you want to make any steels or any cast iron, you need to first understand the phase diagram, and based on that, you have to determine the composition. So again, depending on what composition you have, depending on the content of your carbon, your microstructure of that material will change, right? So if you have eutectoid mixture, you here exactly at 0.76 carbon percent, you get these typical perlite structures, right? Microstructures. And here is a nice diagram I found on the internet. So here is the microstructure directly overlaid on the phase diagram. So perlite is somewhere here, and this is cementite. So again, this is the temperature here, and if you go from here to here, you can, if you quench or do any thermal treatment, you can change the microstructure. I showed you in one of the slides, I showed you how the ductility decreases as you go from, ductility increases as you go from martensite all the way to austenite, and the hardness increases from austenite to martensite, right? So, but if you take a martensite and anneal it, you may change its microstructure, and hence you can change its properties as well. Okay, so here are the uses of different different phases of this iron carbon alloy. So at very low carbon content, you make use of this material for electromagnets, and somewhere here below 1%, that is below 0.8%, you make use in gears. Springs is about 0.8%, and so on and so forth. All the way here at 4%, you have cast iron. So these are different applications for of this composition. The applications are determined based on their properties, and the properties are determined based on the microstructure. So if you have certain type of microstructure, they allow dislocation motion in a certain pattern, and which will change the yield point or the mechanical properties accordingly. Okay, so the alpha ion is about BCC structure, whereas gamma ion is a face-centered structure. Delta ion, which is at a very small composition range, is again a BCC, body-centered structure. And let me ask this question. So which crystal structure will be more ductile, face-centered or body-centered or simple cubic? Why simple cubic? So when you say ductile, that means uh, has plastic deformation. So it's not brittle. It doesn't abruptly break. So, but then you have to ask a question: what is plastic deformation, right? So, how does lattice help in plastic deformation, or how lattice influences plastic deformation? Sorry. So face-centered cubic structure will be more ductile. The reason for that is because face-centered cubic structure will have more slip planes. So the dislocations will be able to move easily in face-centered cubic structure because you have more layers and more um, options to for the dislocations to slip. So when dislocations slip, you get plastic deformation. Okay. So now we already talked about ferrous and non-ferrous. So metal alloys are ferrous and non-ferrous, broadly classified as, but it should be, I think it's very steel-centric classification. I mean, why only? It's like saying only iron and non-iron based materials. No, but anyway, that doesn't. So this is how usually it's classified: ferrous and non-ferrous. And in ferrous, you have steels and cast iron. Cast iron, 4% or more carbon content. Steels, less than 1.5, less than 2% of carbon content. And within steel, you have um, low carbon steel, which is below 0.5%, and medium carbon and high carbon. High carbon is above 1%. And again, in low carbon, you can have plain or you can have high strength, low carbon steel alloy. Same here. So you see that, right? First, the composition determines whether you are ferrous or non-ferrous. Same here, steels is also determined by composition. And then within your composition, but here your thermal treatment makes it whether it is heat treated or high strength or stainless steel. Okay. Yeah, I think stainless steel is not just uh, in high strength alloys. You have stainless steel because you have additional elements in the steel. In iron and carbon, you add something else to get stainless steel. And these are, here you come, these are useful for tools. So what are different techniques, metal fabrication techniques? One is forming, casting, and miscellaneous, right? So the first one is forming, and in forming, you have various techniques. One is forging, just you hammer it at a high temperature, you get the shape you want. Stamping or hammering, you basically use, in stamping, you use some sort of die, and you press on it, and then you get the shape you want. And the um, wrenches and crankshafts are some of the examples which are prepared using uh, uh, forging, especially stamping. And within forging, forming, not forging, within forming, you have rolling as well. In rolling, you reduce the dimension of the material you're using two rolls. So this is for sheets and plates, rails and I-beams. These are prepared using rolling. It can be cold rolling or hot rolling. This is one way to make a required shape. And when you do this, these processes also alter the properties, mechanical properties, to some extent. And drawing is similar to rolling, but here you have a specific shape of die, and you draw. It could be circular or it could be certain shape. You use tensile force to draw it, whereas dies stay in the same place. Here roll the material to reduce the dimension. There also you reduce the dimension, but there you don't, dies don't move. Here rolls move, and there you use a tensile force. So it's not responding properly. Okay, so the last one is extrusion. Extrusion is using a ram in a specific constrained geometry with a die. So here you extrude a material. These are done for rods and tubes. So this is for ductile materials such as copper, aluminum, and it could be for aluminum, it's normally done in higher temperatures, which is um, so these are different type of fabrication methods. Now let's go to another type of fabrication method or forming method, which is casting. Another type of fabrication method, which is called casting. So in casting, you basically have a mold and you fill that mold. So these are inexpensive. You fill the mold and remove the mold, and you get a certain shape. So this is inexpensive, and it gives you can have complicated shapes, but the product finish is not that good, and it's good for brittle materials. You can also do ductile materials, but ductile materials have more options, which is you can do extrusion, rolling, and so on and so forth. So normally casting is for materials such as cast iron and other brittle materials, including some ceramics. Okay, so there is sand casting, which is quite widely used. And you can do with sand casting, you can cast large parts, and you can cast materials that have high melting temperature, higher than 1600 degrees centigrade. Um, so this is another way. So then there is investment casting, which is um, using wax. So there are different stages. Again, it's straightforward how you have a die, you fill the wax, then you get a mold, and you fill that with molten metal. So you get a shape that you want. And then there is die casting, which is this is used for for high volume. So usually automobile parts are done with die casting, especially aluminum, wherein you mold the metal, put it in two dies. Usually they are two parts, and you fill it and you separate it. Because they're in two parts, some surface finish at the parts where there is mold separation, you need to do some post processing there. But that is also another less expensive and high throughput process. And another one is called continuous casting. And then you have miscellaneous, which includes sintering, powder metallurgy, and so on and so forth. Okay, so these are different types of uh, processing techniques. And why are we looking at this? Because you will be using additive manufacturing, so you have to understand how additive manufacturing or 3D printing is better than these ones. If it's not better, then you already have existing techniques, right? Or um, um, yeah, and you can see what are the limitations here. Some of these limitations can be overcome by additive manufacturing, especially for complex shapes. And also you can uh, compare and contrast and see which one is a better technique, and how you can, if there is any way you can improve any of the processes, you can do that, provided you know all these techniques. Okay, so in powder metallurgy, you basically mix the material according to the stoichiometry, and then press it and heat it. Okay, so that is sintering. That's called sintering. When you have, for example, if you want to make ferrite material, so iron oxide or cobalt ferrite or zinc ferrite, so you mix all these materials with the needed stoichiometry, and then take the powder, press it at a high pressure and high temperature. Then you get a reaction as well as densification. This is another technique for making different structures. Then we have welding. Welding is when you usually use uh, two pieces together by melting the interface. That's another process. Um, so those all probably we're all familiar with those techniques. And so I just wanted to show you those different processes. But now let's look at some newer um, processing techniques. Okay, so this technique is called melt spinning process, wherein you make a material that is amorphous. You don't allow the material to, you don't give enough time for the crystals to form in this case. So what happens is, when you pour the molten metal on a spinning wheel, which is maintained at a very low temperature, and that is done using water circulation. So when the metal is poured on this cold spinning wheel, it solidifies rapidly, and that solidified material is pulled through more cold bath containers. So you don't give enough time for the molten metal to form crystals. So you get a amorphous structure for um, this kind of material. And it's has anybody heard of met glass? So glass is because it's amorphous, like glass, it's not crystalline. met is metal glass. Okay, so it's a word coined by Hitachi Metals. So they patented this technique for making um, electrical steel for transformers. Okay, this met glass has amorphous structure which improves the magnetic properties, soft magnetic properties, significantly, and reduces the coercivity. So this is one of the high permeability, low coercivity um, magnetic material. Okay, so when you get uh, the ribbons out of this molten process. So when you look at this, this is how they look like. And this is still metallic in appearance. It's shiny, and it is strong, but it's amorphous in nature, and it's not crystalline. So if you take it to XRD, what do you see? If you take XRD measurement on this, what do you see? Any answers? So you remember XRD will have peaks that represent different planes of a crystal. There is no crystal here. So there is, sorry? There won't be peaks. Peaks come because when you remember Bragg's law, when two X-rays by meet that are separated by d lattice parameter, n lambda equals 2d sine theta. So there is no d, there are no planes. So for peaks to occur, those X-rays have to constructively interfere. So now there is no d in the Bragg's in the lattice. So there is no constructive interference to form one line. So there can't be peaks, but you will just get, somebody said a flat line. It won't be a flat line, but you get some hump. Okay, so that's what you see in XRD. Right, so this is a quite energy intensive process, right? Because you have to heat the material to a very high temperature and then rapidly cool the spinning wheel to get this amorphous material. So these are not just for magnetic materials. There are other type of met glasses as well. So they are used for many niche applications. So anywhere you need amorphous metallic material, um, there also sometimes, if you, depending on the time of cooling, sometimes you get nanocrystalline structures. The grains will be so small that if you allow a little bit more time to cool, they form very small crystallites, grains. So those are called nanocrystalline materials. Okay, so if you don't allow any time, it becomes completely amorphous. So here is the properties of amorphous alloy ribbons. Their benefits is high saturation induction, so high saturation in magnetic materials, and low coercivity. So low coercivity is good for electrical steels. That means transformer, when it oscillates with 50 hertz, there is no heating. Low core losses. This is again, you remember I talked about humming noise. So that is due to the magnetostriction that increases the core loss, and that core loss can be reduced with these kind of materials. So, and you can have variable permeability by doing different heat treatment. So that means you can increase the permeability by additional heat treatment, or you can leave it as it is, but it will have slightly low permeability. And they have excellent thermal stability. Okay, so these are the, well, the saturation BS or magnetization is 1.5 Tesla, which is quite high. And uh, all these are basically good parameters, right? So the Curie temperature, 410 degrees centigrade, is quite high. Crystallization temperature, 536. We rarely go to that temperatures. Before we go to that temperatures, oils or anything that you keep for cooling will boil off. So saturation magnetostriction is very low, 27 ppm. Okay, so low magnetostriction means low humming, and resistivity um, is also low. For electrical steels, you want to have lower resistivity. Actually, not too low, because if you have too low, then you will have eddy currents. Okay, so, and again, I don't want to go over all these parameters. What basically this slide is showing is that you can, many properties of met glass or nanocrystalline material is far superior to the regular polycrystalline material. Okay, so you can also do the same thing. Instead of ribbon, you can make nanocrystalline or amorphous wires, and they also have different applications. So these are somewhat unique processes, probably that are not uh, widely used in many applications, but these are also new techniques. So amorphous materials were not widely explored before, but they have good mechanical or good magnetic properties that are quite useful. Um, and you can also tune their um, electrical properties by heat treating. Okay, so now that's amorphous, and the previous techniques we saw, what kind of material does it produce, like forging, forming, or casting? Um, what type of material it is in terms of crystalline, amorphous, single crystal, polycrystalline? So a casted material is what kind of material? Polycrystalline, right? It has grains. And the previous one is amorphous, where there is no crystallinity. You can have nanocrystalline material, but now the next one is single crystal material. Okay, so what is the difference between single crystal and polycrystalline material? We went over it, right, quickly in the first. Sorry. No, we are talking about single crystal and polycrystalline, right? Yeah, single crystal and polycrystalline. What's the difference? Okay, and how does it translate to properties? Yeah, single crystal and polycrystalline, yes, the name suggests, okay, one crystal all aligned, polycrystalline, smaller crystal misaligned. But how does it translate to properties? That's correct. So single crystal, you get anisotropic properties. That is, along one axis you have different properties, and along other axis you have different properties, right? Properties change along different axes. But what about polycrystalline? It's not anisotropic, right? It's isotropic. You get same property because of the random orientation of grains. You get, unless you texture it. Okay, if you just cast a material and take it out, the casted material will be polycrystalline and will have no, it will be isotropic. Okay, so single crystal materials are anisotropic, but what about the properties. Will the properties be better than single crystal, or sorry, polycrystalline, or where do you find the properties better, polycrystalline or single crystal? So for example, if I take electrical conductivity, is electrical conductivity better in single crystal or polycrystalline? Single crystal, right? Because in polycrystalline, you have grains that impede the motion of electron. Likewise, the mechanical properties, the grains will act as pinning sides or will impede the motion of dislocations. So you will have higher yield strength, so they are less ductile, more brittle, right? Whereas single crystal will be more ductile for the same material. Okay, so there are several ways you can make single crystal materials. The most popular one is called Bridgman method, and the other one is called let's see, can anyone pronounce this? Tchaikovsky. Have you guys studied Tchaikovsky? Okay. So that's Tchaikovsky. It took me a while to pronounce and remember that name. So this is named after Jan Tchaikovsky, who is a Polish metallurgist. So this is another method of making single crystals. Then there are other ones. There is one more that I don't see, is called tri-arc pulling method. So basically, if you look at all these techniques, what they do is there is a well-controlled temperature zone, and then you need a seed to initiate the crystal growth. And however you orient that seed, and the crystal will start growing in that direction. Okay, so in order to accelerate the growth, some processes will start pulling the crystal out of the molten bath. Okay, so some have different mechanism to pull. But the basic idea is take a molten material, use a seed, and make the material grow using that seed. Okay, so you get a single crystal sample, and each of them will result in, they have certain, I think Bridgman won't give you bigger than 10 centimeters of, again, it depends on which material you are growing. Okay, so there is also another one called flux, forgot. If you want very small single crystals, there is another technique called, again, I can't remember, something to do with flux method. So that's another method. There are varieties of methods, but the main idea is, but they all start with a seed. Okay, you get a single crystal using these methods. So here is a single crystal after ingot after you grow. Um, uh, this is from silicon. So this is a silicon single crystal ingot. Usually in the middle you have perfect crystal. Sometimes you can have at the edges some misalignments, or you might get one or two grains instead of one single crystal. So this is how the single crystal silicon is grown. So where do you need such a material, single crystal silicon? Semiconductors, yes. Silicon wafers, it looks like it's 6-inch wafer disk, right? So silicon wafers for most of the electronic devices, you need a silicon wafer, and the silicon wafers are then sliced from this silicon ingot, single crystal silicon ingot. Of course, it's first machined to a exact cylinder, and then the discs are sliced. And this is also how you get the solar cells. Remember, earlier solar cells were spherical, circular. It's two-dimensional, circular, right? And nowadays you can get square as well. But this is how the solar cells are made. And that's why they are expensive, because you need a single crystal, something like this. Okay? So that's now the other processing method is thermal processing, which is annealing. So what happens when you anneal any metal? If you heat it up, but you have to heat it up to a certain temperature for annealing. Does anybody remember what's that temperature to anneal? 0.6 times the melting temperature, right? That's when you get recrystallization. But there are all types of annealings. But if you want to recrystallize, or you want to refine the grains or refine the crystals, then you have to go up to 0.6 times the melting temperature. So annealing reduces the dislocation density because you give enough thermal energy for the dislocations to move, and opposite dislocations. Dislocations can be clockwise vector dislocation and counterclockwise vector dislocation. And when clockwise and counterclockwise dislocations meet, they annihilate. So that's why when you increase the temperature, you're basically giving thermal energy and the dislocations move around. And when a counterclockwise meets with the clockwise dislocation, they annihilate. Okay, that's how by annealing you are reducing the dislocation density. Okay, so this is used for reducing the stress relief because you are reducing the dislocation density, which is useful for plastic deformation, and you can also have phase transformation. So that is stress relief annealing. You also have spheroidized annealing, which is normally for steels. This is where you make steels soft. By doing that, you change the morphology or the microstructure of the steel, and that is spheroidized. Basically, you are introducing a lot of spherical microstructures in the steel. So then you have full annealing, which makes steels very soft, and it's good for forming and other cold operations. And then normalize. So these are all different annealing techniques that you can use to basically tune the properties of materials the way you like. Okay, so now comes composite materials. So now we looked at ferrous and non-ferrous, and among ferrous there is, first you vary composition to get cast iron and steels, and then you use different type of forming on different type of steels. So you looked at different type of forming, or not forming, different type of processing of the materials. And we also looked at how to grow a single crystal, or what are single crystal materials. And now let's take a look at another processing technique, which is called making composite materials or composite formation. So for that, you need to know what is composite, right? So composite material is combination of two or more materials. And when you put these two or more materials, the resultant material should have better um, properties than either of the individual materials. Okay, so to obtain a more desirable combination of materials, so this is principle of combined action. Example, if you want to have a low density and high strength, so fiber reinforced composites. um, so Boeing 787 Dreamliner is 50% of it is made by composite materials. Composite materials are becoming very popular. So I think the in the future we will deal with more and more composite materials. Okay, so but making composite materials is not easy. Okay, it involves a lot of um, special techniques. We'll look at some of them, and you get desirable or better properties using composite materials. And especially for structures like aircrafts, where you need lighter but more stronger materials, then you make a composite material. So here is a, so this is um, 787 body, Boeing 787. So it's a large aircraft. And you can see that 50% of its body is made of composite. All this is composite. This is composite. And so the alloy is titanium material, which is mainly the turbines. Red is the aluminum, which is the radar part of the wings. Is it called radar or aerofoil part of the wings? And then steel is the turbines, jet engines, casing, and rest, the whole body, 50% of it is composite. Okay, so more and more composite is being used. This is a book on composite materials for aircraft structures, and the cover of the book has a graph, which is unusual. So you can see here, this is the year of introduction. This is 1965 all the way to 2020. And this is the amount of structure is composite, percentage of structure is composite. You can see that I think this book is published between 2000 to 2000, around 2005, because where it stopped here. There might be many more here. Okay, most of the new aircrafts will fall somewhere here, about 40 to 50% composite. Okay, so and we talked about why what is one of the biggest limitation of composites. So if it's that good, if the material properties are better, why not we all use composites? Yeah, unpredictable. It's very difficult to predict the strength or other properties of a composite material. Okay, so, and this is Airbus A350. Okay, so there you have 52% composite. Okay, Airbus A350 has 52, Boeing 787 has 50%. So more and more aircrafts will have higher and higher percent of composites in the coming years. What do you think about Formula One car? How much do you think has? It is it's a lot of it is composite. Sorry, above 80. Again, I don't know. I just asked you. Yeah, it's a lot, okay? Because if you think about it, the IC engine, well, nowadays there are electric Formula One cars as well. The IC engine can't be composite. Well, you can have composite because right now I think it's IC engines are non-composite. It's alloy, some aluminum alloy. The whole body is composite, um, except the transmission and the wheels. Tires are composite again, right? Tires, because tires have fibers, rubber, and sometimes even the fibers can be metallic fibers as well. Okay, so here is, how many of you have heard of solar impulse? This was a big thing in 2010, I think, 2010 or 2012. But anyway, Airbus is an aircraft that's made out of completely out of composite. I think it's 100% composite, if I'm not wrong. But this, yeah, I wouldn't say 100% because solar cells can't be composite. Um, so it doesn't have any fuel inside. It only has a battery and solar panels. So it took off and went around the earth one full circle without consuming a single drop of fossil fuel, just on solar panels. Okay, so its wingspan is 72 meters, which is huge. 72 meters. And then its weight is 2.3 tons, which is it's not at all that high, which is about weight of a big car, SUV car. And the number of solar cells were 17,248. That doesn't mean anything. If they gave the wattage, it would make sense. So number of propellers and batteries is 4. So the total energy produced from Abu Dhabi to Abu Dhabi is 11,655 kilowatt hour. So fuel consumed is 3. This was a big milestone. An aircraft went around the earth without using any fuel. Okay, so of course they had to make the aircraft almost more than 90% composite. Okay, so here is a video of how they make this aircraft.
"72 meters long, covered in solar cells, ultralight, and allowing Solar Impulse to fly day and night. This is the Solar Impulse wing. An extraordinary flight called for an extraordinary wing to be built. Wider than a Boeing 747, Solar Impulse 2 has
device or new cool structure or new cool machine that will have composite materials. So you although it's difficult to make them and predict their strength and predict their properties, but that's the way to go. So now you need to identify how best to estimate their strengths, right? So um, where else do you see composites? Okay, one Formula One car we talked about, aircrafts we talked about. Where else do you see composites? Yeah, wind turbine blades are composite materials. Okay, so they're so big, especially the offshore ones that are in the sea. They are so big, and if you make out of any metal or any other material, it they're going to collapse on their own weight. Okay, it has to be made out of a composite material. And I think with this, even the propellers in this were, I think, composite. I read somewhere that even the propellers that they used for their engine, the motors, were composite. Okay, so composite is the way forward. I mean, in the future, you will see more and more composite. So you have to identify processing methods, determine estimating its properties or measurement of its properties, how you measure it, and the next one is how do you 3D print them if they are complex structure? How do you 3D print a composite material? Okay, we are still learning 3D printing normal material, but imagine composite 3D printing composite material is even more challenging. Okay, so I'll quickly show you what are different type of composite materials. So in composite materials, the terminology, again, if you have done material science class, you might have come across these, but this is fundamentals of composite materials. So multi-phase material that is artificially made. So the nomenclature is the matrix is the thing that is continuous, and the dispersed media is the one that is discontinuous. That is usually the dispersed phase is added in the matrix phase. Okay, so you have matrix phase and dispersed phase. Matrix phase is the continuous material, and the dispersed phase is a material added to matrix phase in order to improve certain property. Okay, and here are different types of composites. So you have, depending on what is your dispersed media. If your dispersed media is particles, it's particle reinforced. If it is fiber, it's fiber reinforced. And you can have structural dispersed media as well, which is like laminates and sandwich panels, honeycomb structures. These are all structural composite materials. Okay, so again, within particles, you have large particles and the small particles. In fiber, you have continuous and discontinuous, and within discontinuous, you can have aligned and randomly oriented. So which one do you think will have higher strength, aligned or randomly oriented? I beg to differ. Randomly oriented will have better strength because when you try to break it, any small cracks can propagate alongside the aligned fibers, whereas randomly oriented, each fiber is stopping the crack propagation, right? So it is randomly oriented, have better strength. But aligned is easy to predict the property. Okay, so And then in structural, you have laminate. We talked about that. So particle reinforced, the most common particle reinforced composite is cement or concrete. Here, this is another this is cementite. In this material, you have ferrite, which is Fe3C, embedded in cementite. So a ferrite, that is Fe, embedded in Fe3C cementite. So this is, again, one of the phase of steel that is nothing but a composite material, right? Because you have one phase embedded in the other phase. So it is though it's a mixed phase steel, but it's a composite material. So you have other materials as well. These are, we are now talking about metals here. This is tungsten carbide. That is, so these are different type of particle reinforced composites. And then we have fiber reinforced composites. Here, this is carbon-carbon fiber, and you can have different types of fibers as well. So this is fiber reinforced composite. Then we have, so yeah, the one way to make fiber reinforced composite is called pultrusion method. So basically what you do is you take the fibers, draw them into the matrix phase, and then you cure it, and then you press it in the rolls. So that is a fiber reinforced composite. And this is one way to make fiber reinforced composite material. Okay, and then the other way is filament winding. And when you wind, you add the matrix phase. So the matrix phase can be any resin. So the filament, depending on what kind of strength you want, what is your targeted property, you use accordingly a desired filament. And then we have structural. In laminates, you take laminates and then stack them together in multiple orientations to give you a better strength. Or you can have 3D structures like honeycomb or some other parameters as well. I had another video. So this is the video that you saw, or solar impulse, right? This is perfectly or a success story of composite. Do you know any failure story of composite? Here, yeah, they got it right, everything worked out. Composite allowed them to fly around the world. But what about, are there any instances where composites failed miserably? So of course, composites, it's difficult to predict the strength. And if you can't predict it right, you can have failure, right? Some of the wind turbines failed. I wouldn't call it miserably failed. It's okay. There are instances of failure. But have you heard of Ocean Gate? Yeah, submarine, right? So this submarine was built to go to the floor of Atlantic Ocean where Titanic sank. Okay, so this submarine went to see the Titanic. Of course, there were people in it. Went to see the Titanic, and they came up with this composite material that they think can withstand, but it imploded. Okay, all the 5 people or 4 people on board instantly died beyond recognition. So I have a video on that one. I really want to show you that because you come to know, because there is a discussion on composite materials, how it failed. Well, concrete is composite, yes, but it's a well-established composite. I mean, if we're talking about new composite, concrete is so tested so much. Yeah, we know strength of concrete very well. Yeah. Solar impulse. Yeah. Oh, that was okay. So you can still do that, but the problem is the speed is very low, and also such a high wingspan is not practical to store it and operate from different airports. Okay, so it's to demonstrate. I think that's a good demonstration that shows us that yes, renewable energy. I think, frankly speaking, after they demonstrated, I think the focus on solar energy became um, more important, or the people started to take note of it. If a airplane can circle around the earth without a drop of fuel, that means we can use solar energy. But also they had advantage. The solar cells that they used were the efficiency of those solar cells were much higher than 20%. And also when you fly above the clouds, you get the best solar light. Okay, so your solar, um, it's called solar factor, is 1. So here, when we below the clouds and dust and smoke and pollution, there is something called solar dimming. Yeah. So uh, you can't get the same level, but it shows that there's a lot of potential. Yeah. We still need to increase the efficiency of solar cell significantly to make it even for cars. For example, an electric car, if you find a solar cell that is about 50% efficient, I think you can cover a car with all solar cells and drive it and charge it by solar energy itself. But so the solar cell efficiency is about 12 to 14%. What we have now. These are single crystal silicon solar cells. There are something called tandem solar cells, wherein they are sandwich of different types of solar cells. Those have much higher efficiency. I think they go up to 25%. Yeah. So they constantly improve the solar cell efficiency. Perovskites are another type of solar cells, but their perovskites are slightly heavier. Um, any other questions? So that means now you know the basic material science concepts, you know different type of materials, functional materials, you know how to process them. So given any problem, you should be able to at least theoretically come up with a solution, right? If not, make it. Now, once you learn about 3D printing, you should be able to make. Okay, so we are finishing a little early today. If you don't have any questions, we can, yeah, break for coffee or, yeah, and then you can spend that time on your projects. Okay, thank you. I'll be around if you have any questions.
No questions? So no one dare to go again after that question gate.
Right. which is the deepest part of the earth. Yeah, 9,000 meters is about 9 kilometers, which is taller than Mount Everest. Yeah, so he went there, but his submarine was a proper titanium, very well equipped submarine. But this guy wanted to make an industry or a business out of going down to certain depths. So this is what happened.
The company closed or still?
Yeah, no, not just closed. People sued it. So, yeah, he was on the Times cover at one point.
Yeah. I think all billionaires want to see at least,
Yeah,
or maybe not billionaires, crazy people want to see that.
see, he had the power to convince people.
Okay.
So, actually, he convinced.
So you said they had a fight with?
Yeah, more than that.
Nothing happened during.
No, every time, the problem was every time they went down, there was small crack or small delamination of
When they came back. This
Yeah.
time they did not come.
yeah. So the last time the delamination accumulated, it completely imploded. So, yeah.
Why silver rate is daily increasing by 5,000? What is the reason?
Availability of material. No?
I have.
What is the main reason with respect to this one?
Which material is that?
Silver.
Okay.
Every day it is increasing by 5,000.
Okay. So people are actually going after silver, not gold now. Very simple. Because
Yeah.
can I answer that?
Yeah, sure.
So there is this thing that now I think the many so now people don't want to spend money on a gold because it is too expensive, man. And but people they just want to wear it or they just want to feel it and then they want to actually